Okay, let's think about this for a second. How do we really know what something is? I mean, down at the molecular level. How can a scientist in a lab tell two identical-looking clear liquids apart? Or figure out what some mystery powder at a crime scene is? Well, it turns out molecules have this kind of hidden language, a way of telling us exactly who they are.
And that really is the big idea here. What if every single chemical compound had its own unique, completely unmistakable signature, just like a human fingerprint that we could actually read? Well, guess what? They do. And the incredible technique we use to read it is called infrared spectroscopy.
You know, this need for a positive ID is absolutely everywhere. Is this new drug from the pharmaceutical company pure, or is there a dangerous contaminant hiding in there? Is that powder found at a scene something harmless, or is it illegal? Getting the right answer and getting it fast is one of the most fundamental challenges in chemistry.
And this is the incredible promise of infrared or IR spectroscopy. The chart it spits out, called a spectrum, is so specific that it's known as a molecular fingerprint. If the spectrum of your unknown stuff matches the spectrum of a known chemical, they are the same compound. End of story. So how does this amazing technique actually work? Well, it all comes down to a little dance that every molecule is doing all the time.
So let's pull back the curtain and peek at what's happening on that tiny atomic scale. It turns out those bonds holding atoms together inside a molecule, they're not like rigid little sticks. Nope, they're constantly moving, and that motion, that's the key to this whole thing.
Just picture any molecule you can think of. Those atoms aren't just sitting there frozen in place. They're in a constant super-energetic dance. They're stretching, they're bending, they're twisting. And these aren't just random jitters. They are very specific, predictable movements that we call molecular vibrations.
Probably the best way to visualize this is to imagine the bonds are tiny little springs connecting the atoms. And this is where a classic physics idea called Hooke's law comes into play. It's actually super intuitive. A stronger bond, which is like a really stiff spring, vibrates at a higher, faster frequency. And just like if you put heavier weights on a spring, it'll bounce slower, bonds between heavier atoms also vibrate more slowly. This simple relationship is the secret to everything.
Now, these molecular dances can pretty much be broken down into two main categories. First, you've got stretching. That's where the atoms move back and forth along the bond itself, almost like they're playing a tiny game of tug-of-war. And then you have bending, which is all about a change in the angle between two different bonds.
And bending itself comes in all these different flavors, with pretty great names like scissoring, rocking, and twisting. Now, you don't need to memorize these. Just know that each one of these unique little dance moves requires its own specific amount of energy to get going.
So, here's the crucial part. How do we actually see these vibrations? Well, we shine infrared light on the molecules. If the light's frequency perfectly matches a vibration's natural frequency, the molecule absorbs that light. But, and this is the golden rule, the vibration has to cause a change in the molecule's overall electrical balance. Think of it as a center of positive and negative charge. For IR light to see a vibration, that vibration must make the electrical center shift. If there's no shift, that vibration is completely invisible to our detector.
And CO2, carbon dioxide, is the perfect example of this rule in action. When it does a symmetric stretch, both oxygen atoms pull away from the center carbon at the exact same time. The two poles cancel each other out perfectly, so no net change in that electrical balance. That vibration is IR inactive. It's invisible to us. But in the asymmetric stretch, as one oxygen pulls away, the other one scoots closer. This creates an imbalance, a net change. And because of that, this vibration is IR active. It shows up loud and clear on the spectrum.
All right, so we know that specific vibrations absorb specific frequencies of IR light, but only if they're IR active. That's all the theory. But how do you actually build a machine to measure this and create that molecular fingerprint? Let's take a look inside a modern spectrometer.
Modern instruments, these FTIR spectrometers, are just incredibly clever. First, a source blasts a whole range of infrared frequencies all at once. This light beam goes right through our sample. The molecule inside just gobbles up the specific frequencies that match its natural vibrations. Whatever light makes it through to the other side hits a detector, which measures what's missing. Now, the raw signal is this complex, messy wave, but a super fast mathematical trick called a Fourier transform takes that jumble and turns it into the clean, beautiful spectrum we need to read.
And this is what you get, an IR spectrum. It's basically a graph that shows us exactly which frequencies of light the molecule absorbed. Along the bottom, you've got the frequency,
and on the side you see how much light got through. Every one of those valleys dipping down represents a specific molecular vibration telling its story.
Okay, we have our fingerprint. Now comes the really fun part, the detective work. How in the world do we read it? An IR spectrum is kind of like a treasure map, with different regions telling us different things about the molecule we're looking at.
The best way to understand an IR spectrum is to split it into two main zones. Over on the left, from about 4,000 to 1,500, we have the functional group region. The peaks here are like big, obvious signposts. They tell you what's in it, what kind of chemical building blocks are present. Then, on the right, you have the fingerprint region. This part is a super complex, messy-looking pattern that comes from the whole molecule vibrating. And it's this part that answers the question, who is it? It's completely unique. So, any chemist will look at that functional group region first. Is there a big, wide peak around 3,300? That's a classic signature for an OH group, meaning you've probably got an alcohol. What about a sharp, really strong peak around 1,700? That basically screams that you have a carbonyl group, a carbon double bonded to an oxygen. It's like a quick checklist. But what if two molecules have the exact same functional groups? How do you tell them apart? That's where the real magic happens.
Just how important is that fingerprint region? Well, take two molecules like propan-1-ol and propan-2-ol. They're isomers. They have the exact same atoms, just arranged a tiny bit differently. If you only look at their functional group regions, their spectra look almost identical. Both clearly show that big OH peak for an alcohol, but their fingerprint regions? Completely different. That one-of-a-kind pattern, caused by tiny differences in their overall structure, is the smoking gun. It's the ultimate proof that lets us tell them apart with 100% certainty.
Now, this isn't just some neat trick for a chemistry class. It's a seriously powerful tool that's being used every single day to solve major real-world problems. The ability to get a molecular fingerprint in just minutes has totally changed the game in countless fields.
Just think about it. Forensic scientists use it to identify drugs or fibers. Drug companies use it to make absolutely sure their products are pure. Environmental agencies can monitor car exhaust for nasty pollutants like carbon monoxide. Chemists can even use it to watch a reaction as it happens, seeing the peaks for the starting stuff disappear while the peaks for the new product pop up. And yep, that breathalyzer that law enforcement uses, it's basically just a miniature IR spectrometer, specifically tuned to spot the vibrations from ethanol.
So, in the end, it all comes back to this one simple, beautiful idea. Molecules are constantly vibrating, each with its own unique rhythm, its own secret song. By shining a little bit of infrared light on them and seeing which notes they absorb, we can listen in. We can read their molecular fingerprints and know, without a doubt, exactly what they are.
It's just a powerful reminder that there are entire worlds of information hidden all around us, just beyond our senses, written in languages we're only just starting to understand. If we figured out how to translate the vibrations molecules, what other secrets of the universe are just waiting for the right tool to help us finally see them?